Hi, and welcome back to another exciting Math 112 lecture. Today we're going to talk about modeling the changing midline and amplitude. And we're going to start with an example, with a couple of examples. So I'm actually going to open up Desmos here because I want us to take a look at what happens when we try to change our midline. So what I have graphed here is a standard sine function. And we know what happens when we change our external multiplier. That makes our amplitude bigger, right? Or smaller, or we can turn the thing upside down. Okay. We also know what happens when we change our horizontal shift coefficient, our b. We change our period. Now, we're familiar with moving this up and down. That's what this b does. But we can also, so this actually says y equals a times the sine of x plus mx plus b. This plus mx, what this does, it actually adds a tilt to my function. So you can see it changes my midline. Now it does more than just tilt it, because look, it kind of skews the function a little bit. And you can see that if we get very steep, pretty soon we lose our oscillations. We might, but then what happens if we change our period and our amplitude? So you can see that my amplitude still behaves the same way relative to my sine portion, and my period behaves the same way. If I increase my b, I get more oscillations. If I make b smaller, I get fewer oscillations. So what we're going to do is we're going to talk about different examples of what we can do here. We can have linear midlines, which is what I've got up on the screen at the moment. We can also put an exponential function in the midline. So this would be something like big A and big B are our usual modifiers for our sine. Then I've added an exponential term back here. So let's look at a midline that is just straight exponential with a multiplier of 2. So this would be sine x plus 2 to the x. So we're going to do some examples here in a minute, but this is something like an oscillating population or oscillating sales. You can see that, again, if we have very much curvature, it doesn't take long for our oscillations to be overcome by the change in the midline. So we want to be aware of that when we're looking at functions. But again, our amplitude has the effect that we would expect it to have, as does our period modification. All right, we can put almost anything in for as our midline function. Here's a quadratic. I can make that a cubic. That's a quartic. Let's see. Here is a cubic. All right, so my point is that we can first identify a midline function, and then we can talk about the sine function that would handle oscillations around that midline. So let's look at an example here. Suppose we know that ice cream sales oscillate annually with the weather. And we can have as many as 60 scoops per day above the average and 60 scoops per day below the average. And the low occurs, unsurprisingly, in January. We're told that this year they sold 20 scoops per day in January. But they've noticed that the population is increasing, so their average sales are growing 5% each year. And the owner wants to predict his performance out for future years. And so we're going to do a model that gives him an equation for his daily ice cream sales after 2 years. Okay, here's how we're going to do these. Let's start by thinking about the midline. So the midline is what's on this graph right here. But let's get to it. An increase of 5% of each year represents an exponential growth. So that means that our sales are going to be equal to whatever we start with. So our initial, this year it was 20, times 1 plus the growth rate, which is 5%, to the t, raised to the t power. So our midline function is given by 20 times 1.05 to the t power. All right. Can we get to our, but that doesn't count our bumps, our jumps, right? That's just our midline. Just our midline. We want to get to the oscillations that go around this thing because we want to know highs and lows. Okay, so let's think about this. We can either use a sine or a cosine. The sine will begin at the midline, but we're told that the low is in January. So we're actually going to use a negative cosine. Okay, and actually our function is going to be negative a cosine bt plus 20 times 1.05 to the t power. This gives our midline. It's going to take our cosine curve and bend it. Let's figure out our period. We know that we're going to go from a low, so let's think about what this would look like without the increase. We would start at a low, go through a midline and a high, and come back down to a low. So that means we go through one complete cycle each year, so our period is 1. Remember that the new period is equal to the original period divided by our horizontal stretch coefficient, which means that our horizontal stretch coefficient is equal to our original period, which is 2 pi for a cosine, divided by the new period, which is 1 year because our time cycle is in years. So our B is 2 pi. All right, so now we've got, what do we have so far? We have sales is equal to negative A times the cosine of 2 pi times t plus 20 times 1.05 to the t power. It's not so bad. How do we get A? How do we get our amplitude? Well, what do we know? We know that we oscillate 60 scoops plus or minus the average, so our amplitude is 60. So this is going to be negative 60 times the cosine of 2 pi t plus 20 times 1.05 to the t power. And let's take a look at this on a graph, mostly because we can. All right, so here's our midline. I've already plugged in our function, which is y equals negative 60 cosine 2 pi x plus, oops, why did I say 20? Oh, yes, plus 20 times 1.05 to the x power. Let's turn that guy on, and here's what we can see. Now, notice that mathematically, if our average was only 20 and we go 60 scoops below, that would mean we were selling a negative 40 scoops. That doesn't make any sense. We just kind of truncate those off and call them 0 days. But you can see here's a picture of your average scoop sales, including all of your highs and your lows. All right, it's really not that bad once you try it a few times. So I encourage you to, there are different examples in the textbook that are similar to these, but I do encourage you to work through all of them so that you can make sense of this for yourself. Let's try another one. This is a power draw. So a power plant has in the past noticed that the daily power usage oscillates between 40 megawatts and 120 megawatts. But the town's expanding, so the draw has begun to increase by 1 megawatt each month. Let's model the power draw after T days. Okay, again, we're going to start with the midline. In this case, the midline is not given to us, but we've got a low and a high. So the midline is going to be halfway in between those. So 120 plus 40 divided by 2 is 80. So our midline, our average is going to be 80 megawatts. And we're going to oscillate to 40 above and 40 below. 40 megawatts above that value and 40 megawatts below that value. That tells us that our amplitude is 40. Okay, so we've got our midline, we've got our amplitude. This increasing 1 megawatt each month, that indicates a linear increase, a linear midline shift. So our power usage is going to be our amplitude, which is 40, times sine or cosine. They don't tell us whether our day begins with a high or with a low. So we're going to kind of assume our day begins with a midline, because otherwise we have to make a decision. So we're going to use a sine, and we'll come back to the period, plus some slope, plus our midline, which is 80. Let's get to this slope. An increase of 1 megawatt per month, but our time is in days. So that means that we actually increase, we're using a linear model, so we're gonna make an assumption here. That means we increase 1/30th of a megawatt per day. So my slope is 1 over 30. So this is going to become 1/30th. And how do I get to my B? Well, I get there by my period. So let's think about what's going on here. I'm oscillating daily. And my X is in days. So my period is 1. We just did this. So that means my B is going to be 2 pi, just like it was in the last example. So my power oscillation after T days is going to be 40, or my power draw at any point, at any day, is going to be represented by P of T, where T is the number of days from whenever we start, times 2 pi T plus T over 30 plus 80. All right. Again, bring any questions to a study session or post them on the forums. Okay, we want to find an equation of this form that fits the data in this chart. Luckily, we are given the horizontal stretch coefficient. So let's start by finding the period. Our new period is going to equal our original period. We're given a sine. So that's going to be 2 pi divided by our internal stretch coefficient, which is pi over 4. So our period is 8. We see, so sine will begin at the midline. We see that at 0, our function value is at 12. So that means my midline, my b value, is 12. So what do we know so far? Not a whole lot. We need to get to slope. How do we get to slope? Well, let's think about what happens here. On a sinusoidal function, we expect our function to be at the midline at t equals 0. And again, halfway through our period is 8. So here at 4, we should also be on the midline. So on the midline, we've got 2 points that are on the midline. They are 0, 12, and 4, 10. That's enough to find our slope. The slope is y2 minus y1 divided by x2 minus x1, which is -2 over 4, or -1/2. So now I've got my m is -1/2. So let's put this together. My function now is y equals a times the sine of pi over 4 times t minus 1/2 t plus 12. To find a, we just pick a point we haven't used yet. So let's try 215. Plug those in. 15 equals a, the unknown, times the sine of pi over 4 times 2 minus 1/2 times 2 plus 12. If you do a little arithmetic and a little bit of algebra, you come to a equals 4. So my function is y equals 4 times the sine of pi over 4 times t minus 1/2 t plus 12. Let's check that real quick. And I neglected to save my graph for this, so we'll build it together. Let's start by putting our points on, just so we can check ourselves. Okay, and we need to okay, there are our points. Now we think that the function that will make this work, so let's just put this in with sliders. Y equals a times the sine of pi over 4. And here we're going to use x for our independent variable, plus mx plus b. Add in all those sliders. Okay. Let's start with b is 12. Oh, that's promising. We got that point. Let's go to a slope of -1/2. Ooh, this is looking better. And now let's see if my amplitude's right. Sure enough, I hit all of those points. So using the tools of mathematics, I was able to find a sinusoidal function that would fit this data table. All right. Now we've talked about changing midline. We can also change our amplitude. So remember how we changed our midline? We changed our midline by adding a function of x back here. Right? Instead of adding a constant, we added a function. That's how we made our midline curve. We can also make our amplitude change. So instead of multiplying by a constant, we multiply by some function of t. And that will allow us to handle all sorts of changing amplitude models. So let's go to Desmos for a minute and let's just take a look at that. So let's work with a sine function. So y is going to equal, let's start with an exponential. So 2 to the x power, okay? But now instead of adding that, we're going to multiply that by the sine of x. And let's look at what's happening. Yeah, you can see our amplitude is getting ever bigger. Let's make this a dampening. There we go. And let's just look right over here so we can kind of see this kind of oscillation describes things like springs and notes, sound that fade away, right? So a spring oscillation, when we include friction, will follow this model. And in fact, let's do an example here of doing this. But I wanted to show you that we can multiply by different things. So let's look at the product of cosine x and sine x. That's not so exciting, but let's change the period of this one. And look at what we got. We got some interesting things. See? What's happening is the amplitude of the sine function is actually being adjusted by the multiply and cosine function on the outside. All right, let's go back here and let's do this last example, and then we're going to stop here because I think I've given you plenty to think about today. So let's say that we are looking at a spring, and unlike previous spring examples, we're going to let friction, we're actually going to model a real world spring. So we've got a spring with a natural length of 60 centimeters. It's pulled either out from the wall or down, whichever way you want to think about that, a distance of 16 centimeters and released. This string oscillates 3 times per second, and after 3 seconds, the amplitude is decreased to 2 centimeters. So here's what we know. We know our oscillation period is 3 oscillations per second. So our period is 1/3. So let's figure out what our function is going to look like. We're going to have a dampened harmonic motion, which is going to be some function of time multiplied by our cosine plus some midline adjustment. Now I picked a cosine because we pulled it out. So at time 0, we were at one end of the curve. We were actually at a maximum distance. So we want to use a cosine. Our period is 1/3. So we need to get to our B. Our horizontal shift coefficient, or our horizontal stretch coefficient, is equal to 2 pi divided by our new period, which is going to be 6 pi. Our B is our midline, which is our natural length, so that's going to be 50. So my little b is 50. We will get to the amplitude in a second. Right now what we have is f of t equals, we know this is dampened harmonic motion, so we know it's going to follow an exponential model. So we're just going to go ahead and put in an exponential model here for my a of t. So it's going to be cosine of 6 pi t plus 50. How do I get to A and B? Well, I've got 2 points on my curve, and they're both related to amplitude. We've got the point, we know what we start with. We know our starting is 16. So the fact that at 0, 16, that gives me that A is 16. We can then plug in another point that is again on the midline, or related to the amplitude, and it tells us the amplitude is decreased to 2 centimeters. So at 3, my amplitude is 2. Now understand these points are on the amplitude function because that was what was given us. This is the distance. My F is distance function or position function. So this is the length of the spring as a function of time. These points are related to the amplitude of oscillation as a function of time. We plug this into our A, B to the T. We find that B is 1/2. And our spring position can be described as 16 times 1/2 to the t seconds times cosine of 6 pi t plus 50. So let's take a look at what that looks like. So y equals 16 times 1/2 to the x power, whoops. Times the cosine of 6 pi x, we'll take care of that in a minute, plus 50. Okay, so we've got all this stuff going on back here in the negative x-axis. We know this is a real world problem, so let's put on a domain limitation that we're only looking at positive x values. This will make it better. Okay, so what do we see? Well, at 0, we can see that our spring was stretched out to 66 centimeters, which is what we expected because we started with 50 centimeter spring and we stretched it 16 centimeters and then let it go. And immediately rebounded so the spring shrunk up, and then it stretched back out, and then it shrunk, and then it stretched, and then it shrunk, and then it stretched, and yep, so you can see what it did. And here we have a graphical representation of this spring behavior, and we can see that it takes let me play with my settings a little bit here and see if I can make that work. Let's just go from -10 to 70. There we go. And you can see that at about 10 seconds, we've finally almost gotten to our spring being still again. It's not really still. If we zoomed in, there would still be a little bit of bounce. But you can see how this works. So this is an example of dampened harmonic motion. Sound will follow this model. Springs follow this model. Remember that bouncing ball that we did in Math 70 when we first started talking about exponential models, the first time you talked about an exponential behavior? Well, you can also kind of model that bouncing ball with this sort of a model. So I will leave this for your consideration. Any questions, please post on the forum or bring to a study session. Have a great day and do good math.